Good afternoon to everyone. Once again, welcome to all. Now, the session will be addressed by Professor Pravat Kumar Rai sir, NIT Rourkela, on the topic Power Management Scheme in a PV Integrated DC Microgrid. Professor Pravat Kumar Rai has received the BE degree in Electrical Engineering from Indira Gandhi Institute of Technology, Sarang, Odisha in 2000, an ME degree in Electrical Engineering from Indian Institute of Engineering, Science and Technology, Sipur, Howrah in 2003. He has received his PhD degree in Electrical Engineering from National Institute of Technology, Rourkela in 2011. He was also a postdoctoral fellow at Nanyang Technology University, Singapore during January 2016 to June 2017. He is currently serving as Professor Electrical Engineering in NIT Rourkela. He has around 20 years of experience in teaching and research. He has supervised 10 PhD students. He has already worked and still working on several R&D projects sponsored by DST, DST Ukraine, Imprint 2, SERV, Indo-Asian, and Indo-Thailand, etc. He co-authored more than 150 research papers in reputed journals and conferences. His research interests include estimation and filtering in power system operation and control, power quality, hybrid AC-DC microgrid, smart grid, solar irradiance forecasting, and renewable integration. So I would like to request Professor Prabhat Kumar Rai sir to address the session. Over to you, sir.
Thank you, Pragya. Hello. So good afternoon, all. So today I'm going to present on the topic power management scheme in a PV integrated DC microgrid. So the main contents of my presentation, before going in detail regarding the power management scheme of a PV integrated DC microgrid, I'll discuss a little bit about what are the requirements for the integration of renewable energy in a microgrid. What are the requirements for integrating storage devices in a microgrid? What are the different power management technologies and comparison among different power management strategies? Then objectives of this power management scheme, the schematic or system configuration. Then I'll discuss regarding current sharing among composite energy storage device. So here I'll discuss a combined energy storage device, that is battery and supercapacitor combined. So how to share current among these two units, that is two methods I will discuss. One is conventional virtual droop control technique, another is improved mixed droop technique, that is the current sharing between or among composite energy storage system. Then I'll discuss active power sharing control between PV, battery storage, load. So this active sharing control scheme, then simulation result, experimental results, conclusion and references. So why we have to go for this microgrid concept? So first is the increasing demand for electricity. This thing I've already discussed during my inaugural address. So nowadays increasing demand for electricity, and also people are more concerned about the environmental effects. So taking into account these two things and also losses due to long transmission line. So there are requirement of renewable integration to the grid so that we will get our power, that is power generation near the load center. So in the microgrid concept, the power generation is near the load center. So that means transmission and distribution cost can be neglected. And why we go for photovoltaic? Because of high efficiency, low installation cost. I've already discussed that is rapid PV development technology, and the installation cost reduces. So more amount of photovoltaic enters into our power system. Now PV system can be integrated, that is in on grid or in off grid, or that is a isolated mode. Now here the main discussion points are what are the main operating differences between the microgrid and a conventional grid? What are the necessity of storage devices, and why we have to go for hybridizing two storage devices? why one storage device is incapable. So what is the necessity of hybridizing two storage devices, that also we'll discuss. Then when there is interconnection of or the combination of two storage devices, then what are the different schemes for this combination? So topologies of interconnection, that is passive, semi-active and active connection. Then I will discuss a comparison of several approaches of this power management scheme. So this is a simple outline of a microgrid. So wind turbine, photovoltaic integrated to the DC bus through their AC-DC or DC-DC converter, battery and supercapacitor, that is combined storage system integrated to DC bus through DC-DC bidirectional converter, and electric vehicle load is there, and this utility is connected to the DC bus to this interlinking converter. This is a simple outline of a microgrid. Now coming to comparison, so all of us know that operating mode in a microgrid is both islanded mode and grid connected mode, but here only grid connected mode in conventional grid. And if we want to control the microgrid, both centralized and decentralized control is there. Individual converter we can control, decentralized control, and centralized control is there, but only available centralized control in conventional grid. And so far as renewable energy integration is concerned, high in microgrid, more amount of renewable is there in microgrid and low in conventional grid. And here we will control the DC link voltage, and here we have to control the frequency. Regarding carbon emission, microgrid, the carbon emission is low, and here in this case high. Installation cost is less in microgrid, high in conventional grid, and power loss is less because the consumer is at the generation point only, so power loss is less, but here more due to transmission and distribution losses. Communication is two-way. That is, for example, when in microgrid electric vehicle is connected, it can act as both source and load. And in our smart grid concept also, we can communicate with the grid. So two-way communication is there in a microgrid, but here only one way. Generation capacity in a microgrid is less, already discussed by previous expert, Professor Premlata Janna. And conventional grid, the generation capacity is high. This is just a brief difference between a microgrid and conventional grid. Now coming to storage devices. So all of us know that when we are talking about renewable integration with the grid, then the main issue is the intermittency issue. So that intermittency issue we can tackle. One of the solution is forecasting, but forecasting here we have not discussed forecasting. In case of forecasting, there are two methods generally. One is model based, another is image based. Regarding model based, taking the previous data, you have to develop and model artificial intelligence model. Based on that, we will forecast what should be our irradiance on this day, this time, like this. But it gives not that much accuracy. Another method is the image based method. That is, we have to capture sky image. Sky image are to be installed. You have to capture sky image within 30-second interval. These sky images in the server, we have to capture it. Then you have to analyze using image processing. If the image at this time is, for example, 3:30 p.m., the image is at this time like this. After 3:35 or 3:34, the image will be like this. So how far is the movement of image? What is the speed of movement of cloud? That is speed of cloud. If the cloud will move at this speed, then after half an hour or 1 hour or 2 hour, 5 hour like this, what should the movement of cloud? If this is the movement of cloud, then which portion of the cloud will cover sun at that time? If thick cloud portion of the sun, a portion of the cloud will be covered by the sun, then there is less irradiance. If there is thin cloud portion will cover the sun, then little bit more irradiance. If clear sky portion of cloud will be covered by sun, then even if more irradiance. So like this, using image analysis, we can determine the solar irradiance or forecast. So that data we can feed also. Okay, so that means beforehand we can know that our solar generation will be this much on this day. So accordingly, we'll adjust our other generation. If this is less, then we may go for other generation. If this is more, we may stop other generation. Like this, we can manage. That is one of the solution forecasting. But here we are discussing to tackle this intermittency issue. Here we have taken the storage concept. So environmental temperature, latitude, longitude of the place also affect power generation. So based on the place, what is this latitude or longitude? So what is the solar irradiance? It will vary. And the situation may create an unbalanced power flow among the loads and generation. So if generation is less, our demand is more, than unbalanced power flow is there, which in turn reduces stability, also reliability. So the design, control and performance of microgrid are still very challenging because of only this intermittency issue of the renewable generation. So to tackle this issue, storage devices give a compromising solution, such as power quality, stability, controllability, reliability of microgrid can be enhanced using the storage devices. So this is the brief characteristic of different storage devices, that is flywheel, supercapacitor, lead acid battery, lithium ion battery, and SMES, superconducting magnetic energy storage, and fuel cell. So different characteristics are efficiency, power density, energy density, lifespan, response time, and cost. So depending on our requirement, we have to combine any two of these storage devices. Then hybrid energy storage system, this technology, HESS technology. So an ideal application of storage system mainly required, we want storage system should have high energy density as well as high power density. It will provide power for a large amount of time for steady state, and for transient time, power for very high power for small amount of time. So we require both the things, high energy density as well as high power density. Our storage device should have high energy density and high power density. But each device has their limitation. That is, due to its limitation, solo storage device cannot provide both these things. In one storage device, we cannot get both the things, high power density and high energy density. That's why we have to go for combination of storage device. So for example, what are the combinations? Here we will discuss regarding combination battery and supercapacitor. So hence it is necessary to integrate two or more storage devices to get a hybrid energy storage system. To get high power density as well as high energy density, we have to go for combination of storage devices. So in microgrid application, it is necessary to combine high power density device with a high energy density device so that it can handle both steady state as well as transient operation. If one device will handle both the operation, then the health of that device may deteriorate. So for enhancing the health of the device and to increase to meet our demand, we have to go for combination of devices. So high energy density based battery storage system can supply average power for a longer duration. Average battery can supply average power for longer duration, high energy density, but supercapacitor will provide high power for small duration. So any sudden changes in the system can cause fast charging or discharging of the battery, so that battery life may deteriorate, which may affect the battery life. So a high power density device is to be added. So that is supercapacitor is chosen to combine with a battery. So supercapacitor will handle sudden surges. Transient part will be handled by supercapacitor and steady state part will be handled by the battery. It will handle sudden surges in the system as its response time is very less. Its time duration is very less, but power handling is high. Battery case is power moderate, response time is very high. So high energy density. So for microgrid application, battery and supercapacitor are combined to construct a hybrid energy storage system. That's why we have to go for hybrid energy storage system. So now it is clear why battery is required or why storage device is required in microgrid, and why we have to go for this combination of storage devices. So now, when there are two devices we have to combine, then how you have to connect it? Based on the connection, there are different topologies. First is the passive connection. So in passive connection, there is no use of any converters. So battery energy storage system as well as supercapacitor directly connected to DC bus. No converter used in between. Here no converter, here also no. Then what is the demerit? The demerit is that the terminal voltage of this hybrid energy storage system should be exactly matched with the DC bus. Its terminal voltage should match with DC bus. Its terminal voltage should match because no converter inverter is there. And that is too difficult. So terminal voltage of hybrid energy storage system should be exactly matched with the connected load and DC link voltage, because this DC link is connected to the load. So its terminal voltage should exactly match with the DC bus as well as with the connected load. So that is the problem. So a lack of control flexibility and sharing of power mainly depends on its internal impedance only. No other thing is there. How much power will be shared by battery, how much power will be shared by supercapacitor, it depends on its only internal impedance in this case. So this is passive connection. Next is semi-active connection. Semi-active connection means one of the storage device is connected to DC bus through bidirectional converter, another directly. Similarly, previous one directly, next one through converter. So both these are semi-active connection. So here converter, a DC-DC converter is there. Here this one directly connected. Here just reverse. So little bit flexibility is there as compared to previous one. Previous one no flexibility, directly connected, and also DC bus is directly connected to load. So terminal voltage of each individual unit should match with the load as well as DC bus. So here, when supercapacitor directly linked to DC bus, the bus voltage fluctuates in any contingency in the system. When it directly connected, any contingency in the system, bus voltage fluctuates. So that means this is semi-active, means little bit flexibility is there, but not total flexible. So next is active connection. So in the active connection, we have to use two converters. See here, one converter is used, another converter is used. One converter for battery, another for supercapacitor, but these are cascade connection. And this is two converters are used, but parallel connection. So this is, so out of all these schematic or schemes, this one is more appropriate, more flexibility is there in this parallel connection. You can individually control each converter, each storage devices converter units. Okay, so the topologies are three types: passive, semi-active, and active. And basically, we have used these topologies in our work. So now, if we'll compare the flexibility, we have already discussed. Flexibility is less in passive. Fluctuation DC bus is there. Space requirement less because no converter used in passive. Complexity is also less because converter are not there. So cost is less, and application in small capacity system where cost is the main determining factor. Cost is less. Semi-active, just medium, everything medium, flexibility medium. This is moderate, voltage fluctuation, space requirement medium because one converter use another for another one, no converter. And complexity is also medium, and cost is also moderate because one converter. And extension of battery life is compromised with slight increase in cost. But this active one, it is high, flexibility is high because two converters are used. You can use controller for both the converters. And fluctuation in DC bus is very less or no. So we can see in the results also. Space requirement is more because two converters used. And complexity is also more. Cost is also high because two converters cost is there. So in a large capacity system, for better transient response, we have to use this one, active connection. Now, power management techniques. So in our microgrid, there are renewable sources, hybrid energy storage system, loads, utility grid, everything is there. Then in order to meet a particular load demand, which are to be active, which are remain to be inactive, which generation, and which storage devices. Always any storage devices cannot supply or cannot take power. It depends on SOC level. So based on this, how to manage power, that is nothing but power management scheme. So here and here it is a two-level control structure. First level, we have to maintain DC bus voltage and current flow in the system. And the second level, proper power allocation to the integrated devices, different integrated devices. We will see all these things. And SOC regulation of storage system are mainly focused. This thing will focus during power management scheme. So different approaches are, first is filter based control, droop control, rule based control, and next is the deadbeat control. So coming to first approach, that is filter based control technique. So here, so we have already discussed the main aim is DC link voltage control. In the previous, that is the first level control, maintain the DC bus voltage, current flow in the system. So we need to maintain DC bus voltage. So VDC reference and this VDC, their comparison, whatever error, VDC error passes through voltage controller. So after passing to this one, this is the total current IT. It contains both this component, means transient part as well as steady state part, or low frequency component as well as high frequency component. Since we have used two storage devices, that's why we have to separate low frequency component as well as high frequency component. So for that we have used a low pass filter. So now whatever available here, this current is having low.
Your voice is not coming.
Sir, voice is not coming.
Sir, voice is not coming.
Hello, now coming?
Yes, sir.
Okay.
Yes, sir.
Now voice is coming?
Yes,
sir.
sir. Coming, sir.
Yes, sir, coming.
Okay. So
Sir.
this VDC reference, VDC, their error passes through this voltage controller, whatever current, that is the total current. This total current having two component, high frequency component, low frequency component, passes through low pass filter. Then the low frequency component current will be shared by battery and grid. Then how much will be shared by battery? How much will be shared by grid? So that depends on this sharing coefficient lambda. That's why you have to frame one rule based on this much SOC, how much lambda should be how much. So that if SOC of battery lies between this percent to this percent, then battery will provide this much power. So this will be decided by this sharing coefficient. So mainly this low frequency component shared by battery and grid, and how much share, that depends on this power sharing coefficient. Then coming to high frequency component, it is shared by this supercapacitor. So that's why this is I supercapacitor reference, and this actual supercapacitor current error fed to PI controller for switching signal generation. Same thing here. Battery reference, sense battery, error, switching signal, and this is for grid. So this is overall filter based control technique, how implemented for power management scheme. Now coming to modified filter. Filter based already over. Modified filter, this portion is modified. This portion is modified. What is this portion? Because of slow dynamics of the battery is not able to track the total reference, that is IB reference. In the previous slide, we have seen that IB reference, whatever we have found out, but because of slow dynamics of battery is not able to track whatever it should track. That's why some amount is left. Whatever left out amount, that is to be means handled by this supercapacitor. That's why this component IB error, I battery error. This I battery error is added with this supercapacitor. Previously, this thing was not there. This part was not there. Only whatever coming, and here I is supercapacitor reference. Now this part is added. So this is called modified filter based technique. Because of slow dynamics of battery is not able to track. That's why for compensation of uncompensated battery current, modified filter based technique was implemented. This uncompensated battery current is supplied by the supercapacitor units to improve system's dynamic performance. This one is the modified. Now coming to droop control technique. In the droop control technique, here we have used virtual resistance droop and virtual capacitance droop. For battery, we have used virtual resistance droop, and for the supercapacitor, we have used virtual capacitance droop. So for optimal utilization of hybrid energy storage system, droop technique is used. Combination of two, that is virtual resistance droop VRD and for battery and virtual capacitance droop VCD for supercapacitor was considered. So here, same thing, only V battery reference, and this IV passes through virtual resistance. This is subtracted. V battery error passes through controller, then I battery reference. Similarly, for this supercapacitor, V supercapacitor reference, and this ISC for this one, 1 by S CV impedance, ISC passes through this impedance, and this VSC reference minus this one, VSC error passes through PI controller, and in this way, reference generator. So in detail also we'll discuss in the previous and the other slides, next slides. So rule-based control. So rule-based control means here some rule we have to obey some rule. Rule means just like we have discussed, power sharing coefficient, how much will be power sharing coefficient? If battery SOC lies between 20% to 80%, this lambda value will be 0.7 or 0.8, whatever. If battery SOC falls below this much, then lambda will be this much. This rule we have to frame, and accordingly our power management scheme will run. That is called rule-based. So in a rule-based control, a sequence of decision-making process is carried out by using present and previous control values. Rules are defined either by using mathematical model of the system or with system expertise. So rule-based control, storage device turned on or off, charging or discharging, depend on SOC limit, how much SOC will be there so that you will go for discharging or charging. All these rule is to be framed. So rules can be defined by considering allowable SOC limit of hybrid storage system, maximum charging discharging rate, total generated power, total connected load. Taking all these things into account, we have to frame rule, and based on this rule, our power management scheme will work. That is rule-based control. Then comes deadbeat control. In the deadbeat control, here main aim is here we can produce an optimal duty ratio. Deadbeat control, we have to find out here optimal duty ratio calculation is there. So we have to calculate optimal duty ratio. Some expressions are there. So after calculating this duty ratio, this is combined with the SAW waveform having this time period TS. Then the control signals are generated for switching of capacitor, supercapacitor, and battery. So this is overall idea how these control techniques are implemented for our power management scheme. So whatever you have discussed, this thing, control technique, filter-based control, advantages, that are the limitations, group control, rule-based control, deadbeat control. So some advantages and some limitations are there for each control. Now coming to power management scheme in PV integrated DC microgrid. Why we are concerned about DC microgrid because off-grid mode of operation, one of the best choice for remote area. This thing already discussed by Professor Premlata Jana also for remote area in the northern India, some parts. So you have to go for DC grid. So in the DC microgrid, gain attention because of fewer conversion stages in a generation. We have already seen on schematic fewer conversion stage in generation. Dynamic nature of weather may lead to introduction of transient. So when transient is there, then which part of the storage device will handle that one? We already discussed that is combination of storage device. Transient part will be handled by supercapacitor. Steady state part will be handled by battery. So to overcome this instability, energy storage devices are integrated. So integration of storage device reduces power fluctuations due to load and generation mismatch. Load and generation mismatch is there, then supply will be given from storage devices. If generation is more, then storage device take like this. So a combination of supercapacitor and battery storage considered in this work, that is called combined storage system or CSS, to enhance runtime of the storage units by reducing stress from the battery. So we'll see how by the combination of supercapacitor and battery and without combining supercapacitor with the battery, how stress change is there. So we'll see in the result. So battery is having high energy density. It can supply average power for a longer duration. And supercapacitor having high power density. So it can supply certain high frequency power, but for short duration. So for safe and smooth operation, there is requirement of a proper active power sharing strategy. So that also will discuss regarding active power sharing strategy. So main objectives of PMS, that is power management scheme, to maintain constant DC bus voltage under different conditions such as variation in generation, variation in load, change in SOC, and enhance the transient power handling capacity by utilizing two storage device combination. Then implement, here I will discuss implement IMDT, that is improved mixed loop technique, how to share power among storage devices, only to share power, that IMDT. So by that, the DC bus voltage recovery can be faster, and will propose novel power management technique to share power, active power efficiently. And this thing will verify using MATLAB simulation as well as experimentation. So this is the system configuration. Here, solar PV is connected to the DC bus through DC-DC converter, and composite storage system, that is supercapacitor and battery, are connected to the DC bus through their own converter. And here is the power sharing control, which supply this duty cycle for operating this DC-DC bidirectional converter and other, and MPPT for this one. So when PV generation is more than load demand, then storage unit obviously go for charging. And when PV generation less than load demand, then storage unit go for discharging. So charging, discharging, and storage unit also depends on their SOC level. If we want storage unit should discharge, but whether SOC level permits or not, that also you have to check. So this is the system configuration. So here we'll see how current sharing among composite storage, means among battery and supercapacitor, how current is to be shared. See, this is the battery side and supercapacitor connected, and combinedly the current passes through this load. Combinedly from battery and supercapacitor, current passes through this load. So this is the equivalent circuit diagram, that is B. Now we have already discussed also, that is virtual resistance and virtual capacitance. So the drop here is IVRV, and here this ISC by SCV. And here this part we will discuss later on, that is IMDT concept. This is the without IMDT, and here IMDT is added. How added, how you are getting this one, we'll discuss in the next slide. So we know that impedance of a capacitor is 1 by omega CV, that is 1 by 2 pi FCV. So when frequency is high, when there is sudden change in the system or change in the frequency, the impedance of CV reduces. When frequency is high, impedance of CV reduces. So impedance of CV reduces means the supercapacitor, that path impedance is less. So supercapacitor unit respond to transient part. Sudden change in frequency means transient part. So impedance reduces. So supercapacitor will respond transient part. And during normal operation, this CV is high because frequency is less. Normal operation frequency is less. So this XCV is high. So high means the supercapacitor will not respond to normal component frequency. So who will respond? Battery will respond. That's why depending on the when the supply is high, means when high transient is there, that XCV is less. So supercapacitor will respond that part. At that time, battery will remain ideal. But in normal operation, that XCV is normal operation, F is less, XCV is high. So supercapacitor will not respond, battery will respond. So the output voltage of combined storage system at the common DC bus, we have seen in the diagram that VBO equals to V reference, minus drop IVRV in that. So V reference minus this drop is voltage here. So VBO equals to V reference minus this drop. VSCO equal to V reference minus this drop. So as the system is designed for isolated DC microgrid, so we have seen in the schematic, only PV is there, load is there, and that storage system is there. So total current from the battery and supercapacitor IB plus ISC equals to IPV minus load. Whatever current required, that is to be provided by these two units. Generation minus demand or load, whatever required, that is to be provided by battery and supercapacitor. This is the equation, power balance equation. Now, assumption, voltage drop due to line impedance is neglected. Here in this analysis, voltage drop due to line impedance is neglected. So now DC bus voltage can be expressed as the VDC equals to, that is whatever VBO, and same as VSCO. Both are connected to DC link. But the main limitation in the conventional droop technique, whatever you have discussed, that is only RV and CV concept. What is the main limitation? During normal operation, the voltage drop due to virtual resistance cannot be ignored. Voltage drop due to virtual resistance is there, that is IVRV. So when the voltage drop in the IVRV is there, then it is connected to DC link. So DC link voltage fluctuates. So whatever load connected, then they experience fluctuating voltage. Are you getting? So DC bus voltage deviation impact voltage sensitive loads connected in DC microgrid. Voltage sensitive loads, whatever connected directly to DC microgrid, they will experience fluctuating voltage because of IVRV drop. So our aim is to compensate that drop. That is nothing but the concept of IMDT, improved mixed droop technique. So hence, DC bus voltage should be regulated properly to ensure optimal operation of voltage sensitive load. That means we have to compensate voltage. V compensated, we have to add. So the solution is compensating voltage should be added to the battery voltage to compensate the voltage drop due to virtual resistance. Whatever IVRV drop is there, that we have to compensate, so that the constant voltage should be maintained at the DC bus, and the loads connected to DC bus, they may not experience any fluctuating voltage. Hence, this concept is nothing but the improved mixed droop technique. So V compensator we have added here. Previously our equation is this one. Now you have added V compensator to compensate that drop. And for supercapacitor we remain silent. Why? Because supercapacitor will operate for very less time. High power, transient period only, very less time. We should not bother for that. So that's why we remain silent for supercapacitor case, but battery will operate for more time, steady state operation. So compensated voltage can be expressed by an integral controller as it is used to reduce the steady state error. This V compensated can be expressed in this way, integral controller only. That is V reference minus VBO, that is V compensated. This is to be added here. So now if we'll add this expression here, then we'll get VV0 equal to this one. So using our improved mixed group technique concept, we obtained the relation VV0 equal to minus this V reference minus RV. Instead of only RVIV, this term will get. So this is shown here. This is shown here. RVS by S plus KI. This obtained from this improved mixed. So now this voltage drop due to virtual resistance mainly affect the system operation during normal operation. See, battery, now we have used this IMDT concept for battery only. And again, battery will operate in different SOC level. That is maybe less than its lower limit, maybe more than its higher limit, or maybe within the SOC range. So main period of operation is that SOC of battery lies between 20% to 80%. This is the main period of range of battery. So this period less than 20%, that is SOC less than the SOC of battery less than 20%, and this SOC of battery greater than 80%, very less time. So will not consider. That means we will consider only when SOC of battery lies between 20 to 80%. That's why in the diagram, two branches are there. One is through RV only, that is when SOC of battery lies at this range, and through that RVS by S plus KIB when SOC of battery lies in this range. You getting? So now this VB0 equals to this expression when SOC of battery lies between this 20% to 80%. But at rest of the time, when SOC of battery less than 20% and greater than equal to 80%, that time same thing whatever previously, only droop technique, not IMDT. So now applying current division rule, battery and supercapacitor current can be expressed as like this. See, in our diagram, in one branch, RV into S by S plus KIV is there. Another branch impedance is, in one branch impedance is RV S by S plus KIV, one branch, that is battery, in battery branch. In the diagram we have seen. And supercapacitor branch, what is the impedance? 1 by SCV. Okay. So now we are using current division. Total sum of these two current is I0. So what is then battery current? What is IB? IB equals to total current into other impedance. Current divider rule. Other impedance is what? Other impedance is 1 by SCV divided by sum of impedance. Sum of impedance is RVS by S plus KIB plus 1 by SCV. This is I battery. So from this we'll get this relation. Similarly, I supercapacitor will be how much? I supercapacitor is the total current into other impedance. Other impedance means this one. Total current into RVS by S plus KIB divided by sum, that is RVS by S plus KIB plus 1 by SCV. So from this we'll get this relation. Current using current divider rule. So this is nothing but battery transfer function, and this is nothing but supercapacitor transfer function. Right. So now from this S plus KIB by this one, if you divide RVCV, if you divide here RVCV, here RVCV like this, we'll get this expression. And this one, on comparing the second order equation, S square plus 2 zeta omega n S, and this is omega n square. Similarly for transfer function of supercapacitor. So now, if we'll compare this with a second order equation, this one, then what is our omega n square? Omega n square equals to KIB by RVCB, and 2 zeta omega n equals to 1 by RVCB. So this thing here, so omega n square equals to KIB by RVCB. From this, omega n equal to this one. And then what is RV? RV is virtual resistance. Its value will be del V DC max by IB max. That is del V DC max, the maximum DC bus voltage deviation divided by maximum battery rated current. So here in this case, 5 volt by 5 ampere, we have taken RV as 1. And now coming to find out the relation between omega C and omega N. So for a stable system, the gain GBS at cutoff frequency should be minus 3 dB or 1 by root 2. That is from control theory. The gain transfer function gain equals to 1 by root 2. That is, if this is the magnitude, if this is the magnitude, this is the frequency, then if this is omega C, then this is 0.707 or say 1 by root 2. So at omega C cutoff frequency, this is 1 by root 2. So that means in the transfer function, we have put in place of S j omega C, and we obtain magnitude equals to 1 by root 2. So from this relation, we will get omega C in terms of omega N. This is the relation. Now, Drup parameter for desired dynamic performance of the system. That is, what is the value of CV? Our requirement CV, RV, KIV, all these parameters, RV already calculated. So CV equals to this one from the second order equation comparison. From the second order equation comparison, 2 zeta omega n S equals to this one, we will get CV equal to this one. And RV already calculated. And this KIV equal to this one. So for a smaller value of zeta, the voltage distortion will be faster, but oscillation is more. And if we go for higher value of zeta, the system response will be slower. That's why you have to make a compromise. So taking different value of zeta, we have found out that damping ratio zeta taken as 0.8. So cutoff frequency, this value 2 pi into F is 1. Virtual resistance 1. This capacitance, virtual capacitance, this value, and this is the integral coefficients we have found out a design. Now coming to active power sharing control. See, we have already derived this GBS transfer function, this GSC transfer function. So VDC minus VDC reference minus VDC, whatever error passes through controller, total current through battery transfer function, this I battery reference. Through supercapacitor transfer function, whatever coming current, it is added with the slow dynamics of battery. That battery, some current is there na, in the slow dynamics of battery, some battery error current. This error current is here also. I battery error current. This is added. These two become supercapacitor reference. Then from MPPT, IMPP. Then what is the load and what is the load demand and what is BB generation? Their difference fed to the this scheme or management scheme, reference current generation. Then SOC calculation, battery supercapacitor, their SOC also fed. And from this, we'll find out this I battery reference, I supercapacitor, I PV reference compared with their actual value to find the error passes through hysteresis current controller for switching signal generation. For battery, supercapacitor, and PV also. This is the control scheme we have used, that is active power sharing control. So here the power balance equation is like this. The generation is mainly PV, their battery, supercapacitor. The sum of all these power should be equals to our load demand, P load. And what, as per the diagram, VDC error equals to VDC reference minus VDC. This error passes through the controller, PI controller. So this is P, this is I controller. This error, VDC error, passes through this PI controller. And now whatever that is GVC into this one. Now what I battery equals to this thing already discussed, GBS into ICSS. And I supercapacitor is this GSC into ICSS plus this one is battery error current. So these two become ISC. So from the figure also this thing we have seen. So now power difference between PV system and demand will decide the operating mode, whether PV is more or load is more. That is PV dominating operation or load dominating operation. That is PPV greater than load, that is PV dominating, and P load greater than PPV, that is load dominating. So coming to PV dominating operation, so from the name it indicates the generation of PV is more than load. So when PV generation is more than load, then extra power who will take? Extra power will be taken by storage devices. Then again storage devices, whether they are able to take or not, that you have to check. So if the when power is extra, then battery and supercapacitor have to take. But if SOC of battery and supercapacitor are below their respective upper limit, if they are below their upper limit, then they can take. That is, they go for charging if their limit is below their upper limit. But if battery is completely charged, means already reached the highest limit, then it cannot take charge, so it becomes ideal. And during this period, PV will provide the battery reference current instead of working in MPPT mode. So similarly, supercapacitor when completely charged, it only supplies the transient power to the system, but without taking the charging current. It is completely charged. It will supply transient power, but it cannot take more charge. So based on all these conditions, I battery reference equal to I battery charging. If SOC of battery lies between its lower and upper limit, then only it can take charge. If already SOC of battery higher than upper limit, then it cannot take charge. So it becomes 0. Similarly, supercapacitor reference and PV reference. Based on their SOC level, they can take charge and discharge like this. That is PV dominating. Next is load dominating operation. Load dominating means the load requirement is more than whatever generation. Then what will happen? The storage device will provide the power whatever required. So extra power required by the load is fulfilled by the storage devices. But again, we have to see whether their SOC is sufficient or not. If SOC of battery is not sufficient and we require power, then what you have to do? We require power, means load is more. SOC of battery is not sufficient. At that time, what you have to do? You have to curtail load. So this type of thing is in the power management. So when for the supercapacitor SOC limit goes below the predetermined lower limit, then it goes for charging state along with supplying the transient power. But if battery SOC goes down the lower limit, some non-critical loads should be curtailed.
6 minutes.
That means battery should provide power, but battery SOC is below lower limit, so it cannot provide power. So only option left is we have to curtail the load. So during load dominating operation, PV always operates at the MPPT. So based on all these conditions, these are the IB reference, ISC reference, and IPV reference. Now these are the system parameters: PV array, battery, supercapacitor. All these are used both in simulation and experimental setup. So this is a simulation result first. That is step change in solar irradiance. So during period 0 to 2 second, so the irradiance is 1000 watt per meter square. Then 2 to 4 reduces 700. Then 4 to 6 it becomes 500. So this is the different power of DC microgrid for various in solar generation. See, this red one is various in solar generation. It varies like this. Then see over this portion 0 to 2, over this portion 0 to 2, the generation is more than load demand. This blue line is the load. When generation is more than load demand, then battery will take charge. So that's why battery and supercar both charging. That's why it below 0 limit. Over the period 2 to 4, see, generation is more than load, but difference is less as compared to previous case. That's why battery charging, but whatever charging is less as compared to previous case. Are you getting? And in this case, from 4 to 6, this load is more than generation. Load is more than generation means battery should discharge. So battery is discharging here. Okay, and all these load change part, the transient part, handled by this supercapacitor, green units, green line. And this is the regarding the VDC, battery terminal voltage and supercapacitor terminal voltage maintained at constant. This is the case for change in load. Previous case, change in generation, more than less like this. But here load change, generation remain constant. Generation remain constant. This one generation remain constant and load varies like this. So over the period 0 to 2, the generation is more than load. So battery undergo charging. But over the period 2 to 4, this load is more than generation. Battery will undergo discharging. And whatever discharging over this period is more. Why? Because here this difference is more as compared to this case. So this is regarding same way behavior of current, and these are the terminal voltages of battery supercapacitor. Now coming to PV dominating operation, that is PPV is greater than P load. Different cases, case 1, 2, 3, 4 like this, depending on the SOC of battery and supercapacitor. SOC of battery lies between lower to higher, and SOC of supercapacitor lies between lower to higher. The way we have discussed, same thing here. Over the portion means here for case I, this generation is more than load, so undergo charging. So same way over the period 2I, 3I, IV, depending on the SOC change, all this. SOC of battery and supercapacitor lies between lower to higher, or which one more than higher, depending on this. These are the parts. And this is about PV dominating operation, and these are about maintenance of the DC link voltage, battery voltage, and supercapacitor voltage. This is the load dominating operation, that is PPV less than P load. That is, for example, if you'll see here in the case V, SOC of battery is greater than lower limit, SOC of supercapacitor also greater than lower limit. So that means both battery and supercapacitor will discharge. Why discharge? Because load is more. So over this period C V, that is this V, both are, that is battery is green and supercapacitor also this one. So both discharge above 0. So in this way all modes are shown. And here you see the when both battery completely discharge V3I, V2I. So battery completely discharged means SOC of battery less than lower limit. SOC of battery is less than lower limit, but our, in this case what happens, 7th case here, SOC of battery is less than lower limit, but our load demand is more than generation. So battery should discharge, but battery cannot discharge since its SOC is less than lower limit. That's why load curtailment, load from here curtail to here. So these are the different operations, and these are the DC link voltage maintenance. Here we'll see by hybridizing the supercapacitor with battery, then how the health of battery improves. That is the comparison of system performance without supercapacitor and with supercapacitor. With supercapacitor is this blue one, and without is this red one. See, rate of change of battery current dIB by dt is very low when supercapacitor is hybridized with supercapacitor. This portion, this rate of change is very less because this is curvy, and this case it is high, red case. So that means, and stress from the battery storage has been reduced if we'll combine supercapacitor with battery. That's why this is curvy like this. So this may increase the lifetime of the composite storage device. Now this is a comparison performance analysis. PV generation variation, another is load variation. So this its performance compared with 3 more controllers, that is in the reference 12, 13, 14, and all this will see that the overshoot voltage overshoot is less, then settling time is also less for this proposed case, and here load variation voltage overshoot load variation case also less, and here also less. So that means performance of this one as compared to other three, it performs better as compared to other three. Now coming to experimental setup, that is verification of this proposed algorithm experimentally. So here in this is our laboratory setup developed in our laboratory. So this thing in detail will show you on day after tomorrow that lab power management in hybrid AC/DC micro. This setup, everything, what are the converters, inverters connected to where is the DSO, all these things, DSpace, all this implementation, how to implement all these things in detail will show you, and results also show you on day after tomorrow laboratory classes. So this thing developed in our laboratory, different converters, sensor circuit, battery, PV simulator, supercapacitor, all these are connected and power management scheme implemented. So this is one of the experimental result when change in PV generation is there. See, here this PCSS we have denoted PL minus PPV. PL minus PPV we have denoted as PCSS. See, when battery started to supply extra power required, see over this person at T1, what happens? At T1, PV power reduced. When PV power reduced, then what about PCSS? PV reduced means this total thing become more. PV this part reduce, total become more. So here at T1, whatever PCSS, now it becomes more, increases. So PV reduces. So then who will take power? Battery started to supply the extra power required by the load. When generation reduces, then battery will supply the extra power. That's why battery from this level it increases, battery. But again T2, at T2 instant, PV power is increased. At T2, PV power is increased. If PV will increase, then it will reduce. PV will increase, it will reduce. At T2, this reduces. So when it reduces, then generation more, load less, then battery less supply, or battery provide less supply. Are you getting? PV whatever, it becomes increases. Previously, whatever PV is there, now generation increases. So earlier, whatever battery supply reduces. This is the, and this is the case for experimental outcome for a sudden change in load. Change in load means this part, PL minus PPV, PL minus PPV. So this is PCSS. So when at T1, DC resistive load is decreased. At T1, load is decreased. When this PL decrease, then this becomes decrease. So at T1, this PCC decrease. When this decrease, then what is the meaning of this PCC decrease? Load is less, generation more. So generation more means battery will undergo charging. Reverse thing occurs at T2. Okay. So this is the case for experimental result, power distribution in different cases for isolated DC magnet. Here, so whatever cases we have discussed, case 1, 2, 3, 4, up to 8 cases in the simulation, this thing implemented, but in experimental verification, case 2 and 3 not able to show because battery above high limit. This thing experimentally means real time, difficult to show. That's why case 3, 2, 3, and this triple I is not shown. But all the other cases are shown. Whatever shown in the simulation result, same thing shown here. Means how this battery supercapacitor changes as per load changes. Now this is the case for mode transition, that is power dominating operation, PDO, power dominating operation, to neutral mode. Then from neutral mode to load dominating, how it changes. So these operation, in one operation everything shown, that is excess PV power is used for the charging of battery, power dominating mode, then transfer to neutral mode. Then how battery become means remain previously, now battery charges, now remain here, battery discharges when this mode changes, experimentally verified. So we have seen hybridization of supercapacitor with battery can extend the lifetime of battery from the result we have already seen. And conventional droop control technique we have modified to improved mixed droop technique. Maximum utilization of storage device happen, and that makes the power distribution smooth and efficient. And because of this DC voltage recovery scheme, DC link voltage is having very less over and undershoot, that we have already seen. And performance, in the performance analysis we have seen this less undershoot and overshoot. And fast restoration of DC bus voltage for different operating conditions we have already seen. Load change, generation change, but DC link voltage maintain constant. So proposed technique verified both using simulation and experimental result. And whatever we have discussed, this thing can also be applied to hybrid AC-DC microgrid. Whatever discussed, that is for DC microgrid we have used, it can be extended to hybrid AC-DC microgrid. So these are the references. Thank you. Any query?
Sir, I have a question. Sir,
Yes. Yes.
sir, you said that there are two sources that energy storage devices are hybridized. Then that you
Yes.
said that capacitor is taking care of transient variations and that steady state variations will be taken by the battery. But how the
Yes.
control will be differentiating these two cases in practical case?
That's what that IMDT we have shown na. When there is transient means when there is sudden change in frequency, that XCV equals to 1 by omega CV. That F, when F is high, then XCV become less. When XCV become less, then supercapacitor will respond. At that time, battery will not respond. And during normal operation, that just reverse. Are you getting?
Okay, okay. Okay, thank you, sir.
Thank you. Thank you.
Any more questions from audience?
From NIT Trichy. Sir, hello, am I audible?
Speak louder.
I'm audible now.
Okay, audible.
Sir, I'm having a question, sir. Like we use this PI controller there in filter control. So while modeling, how we can tune this controller there? Is just hit and trial or some you use some technique to control PID controller there is to set the gain values.
Which one? Which one?
Sir, PI controller you are using in filter control technique.
Yeah, yeah.
So how we
Yes.
can tune that PI controller?
Yes, that I have shown the design value, how calculated KIV. I have shown the different steps. Omega C, omega N, all these different parameter RV, CV, and how KIV calculated. I've already. This is design value, not hit and try.
Okay, sir. Means based on parameter only we have to calculate that value.
What?
Sir, means based on parameters we have to calculate that value.
Yes.
Okay,
These
right.
parameters are designed from this analysis what I have discussed already.
Okay,
All
sir.
the steps and this thing detail. It is this is now published in IEEE transaction in power system. It is in early access. You can find out with my name. You can enter my name and IEEE transaction power system early access. You can find out this paper.
Okay, sir. And sir, one more thing. If we consider the line impedance, then is there any difficulty in modeling?
Yes, line impedance. If you will consider, then more complexity will come. Those things. That's why we have now avoided this thing, because our more focus is on this part, not in impedance controlling part.
Okay, sir. Thank you, sir.
Thank you. That frequency will not impact DC bus voltage. This is through converter. This is used na. So that's why that frequency will not impact the DC bus voltage. So this will respond, supercapacitor will respond, and battery will remain silent and just reverse in the other case. Yes. Harmonic cause, that analysis we have not done now. V compensator, that V compensator, I think that part harmonic may not be added there. That part we have not analyzed till now. V compensator. Yes. Ah. Yes, yes. But I don't think it will add harmonics in the system. But till now we have not verified this thing. Okay.
Any more questions? So if any query, please mail query to sir. So moving forward, thank you very much, sir, for conceptually enlightening us with your valuable time, concepts, and idea on various aspects of power management with PV integrated DC microgrid. Thank you, sir.
Thank you.
To sum up, hopefully all the participants have been benefited by the valuable knowledge and concepts provided by our resource persons in today's session and various aspects of microgrid and sustainable energy management. With this, we are going to conclude today's session. Tomorrow, the session will start at 9:30 a.m. with the talk 9 a.m. with the talk by Professor Arnab Ghosh sir on design of switching converters and power management for microgrid.